So we're going to look in Chapter 10 about buffer overflows, also called stack smashing, also called other names as well. Some of them not so nice. So when people wrote code in assembler, they wrote code in compiled languages like C, Fortran, COBOL, even C++, right? It takes your source code, which is written in text, and then it compiles it into what? Machine language, right? Which is targeted toward whatever the machine architecture is. Now, most of the machines here, I believe all of them probably, but maybe not your cell phones, are Intel architecture machines, right? Cell phones are usually other processors like ARM processors and things like that, right? So usually it's taking a C compiler, running it over C source code. That translates your high-level, source statements, which look sort of, English-like, into the actual machine language instructions, which are loads and stores and adds and multiplies and various things, right? And which show up as machine code, which you see as hex instructions and things like that, right? Now, once that stuff is loaded into memory, some architectures are really good at separating instructions from data, and some of them aren't. In many architectures, instructions and data can reside in the same areas of memory. And there's different areas of memory, right, when your program gets loaded in there. One area and particular data structure that's used, so you've got your main RAM, then you've also got something called the stack. Now, the stack is usually built somewhere out of memory, but there's some additional registers that are used to indicate where the stack is. And those are what? The stack pointer, the base pointer, and other things like that. Right? There's also another one called FP. What's the FP register? I'm out of paper here. What's the FP register? The frame pointer. So we'll talk about what that is. I mean, you really only need to know this if you're going to be writing some buffer overflows, but this is what the stack looks like, right? It's a data structure. So the stack operates like one of those big stacks of plates that if you go into some restaurants, right, they keep stacking the plates down. So you put plates on the top, and then when you want a plate, you take it off the top, right? So it's last in, first out, or what's called a LIFO data structure, L-I-F-O, last in, first out. You push something on the stack, then you pop it off the stack, and it's right there. So for you to get to something down at the bottom, you have to pop off all the things at the top. Now, there are ways to index into the stack and access things directly, right? But the normal stack mechanism is you push and pop. So we've got the top of the stack, and that's usually pointed to by a register. A register is a special holding area where you've got some bits, right, to hold some value. And there are registers that hold addresses, and addresses can be 32 bits wide. They can be 48 bits wide. They could be 64 bits wide or even higher, right? So this is an address register pointing to the top of this stack. Somewhere there's usually a register pointing to the bottom of the stack as well, right? And then there are other registers sometimes that point in here as well. There's a register called the frame pointer, or the FP. Now that's used when you're in a C program or a C++ program or some other one. When you jump to a subroutine, that is, you call a subroutine or a function, what happens? Did I just put this on myself? What happens? Right, we push the address that we're at now on the stack first, and then we jump to that new address. Why do we push our address on the stack? Because that's the return address. In fact, what we put on is the next address, so the address of the next instruction sequentially that we want to execute. So we put back the return address here.
Isn't that a pointer to the new location?
The frame pointer now knows where in the stack our return address is. So normally when we do an exit from subroutine, we do a return. It goes to the frame pointer pulls out this address. It then puts it into what? How do we actually return? We push it into the program counter, right, the PC. When we jump to subroutine, we actually load the address of that subroutine into the program counter, and then we're there, right? When we want to return from subroutine, what does the compiler usually do? It takes this return address from the frame pointer. It's been pushed on the stack. and it stores it in the program counter and says, okay, now execute. Jump to that program address, right? Program counter address. Right. Now, typically, you also save the state of the running, system before you do the jump. So it's also usually you push your return address on here, and then you push your registers, right? So we actually have the saved registers on the stack. The Intel registers are called what? A, B, C, D, right? Or A extended, B extended, C extended, AX, BX, CX, DX, right? So here's your saved registers, right? The original ones on the 8080 were the A, B, C, D. Here's your saved register. That allows you to do whatever you want with the registers in the new, called subroutine, and then they get thrown away, and you get the old values get popped back onto their respective registers, right? And the code to do that is all inside the subroutines. The C compiler puts it in there automatically, right? Now let's say that once we get into a routine, there's some area of memory which gets allocated to hold local variables, right? Inside your C program, if you want to create some integers, you want to create some character arrays or whatever, you say, char array, I want 80 characters in this array, and then you say int B and int C or whatever you want, right? Where do those variables get allocated? After all this stuff, right? And in here. So these are called automatic variables. In C, as opposed to static areas, right? You can actually declare variables that are static, and they get allocated somewhere else. What that means is that they're always allocated, right? But automatic variables are only allocated within the scope of that subroutine or function, right? In C, they're called procedures usually. But when that procedure is active, then these automatic variables are here on the stack, and it does that by actually moving the stack pointer up past them, right? And it allocates them in there. And the beauty is that when you return from subroutine, these just go away, right? They disappear. They have no more meaning, right? Which is kind of cool. Now you can pass the address of variables to the called procedure and all that kind of fun stuff or whatever, right? Now, when you want to smash the stack, what is your real goal? Because we are going to end up overwriting some of these auto variables, right? That's one thing you have to do. In fact, we're going to kind of, really destroy this memory on the stack. We're going to overwrite it, and it's going to end up getting all messed up. What is our ultimate goal? What do we really want to overwrite? And what do we want to make the return address? We want to make it jump relative into the middle of our code, right?